nice for all of us. So we should start now the session for this morning, which is going to be the last one of this workshop. And our first speaker is Sjors Heefer, and he will talk about Randers PP waves. And please take the floor and go ahead. Thank you.
That's yeah. Thank you. All right. Hello, everyone. For those who don't know me, my name is Sjors Heefer. I'm a PhD student at the University of Eindhoven in the Netherlands. And first of all, I'd like to say thanks once again to all of the organizers for organizing this great conference, and also the fantastic training school that we've had before this. And the topic of my talk is Randers PP waves. So this is the name that we gave to a new exact solution to the vacuum and field equations in Tensor gravity that we recently discovered. So this is joint work with Christian Pfeiffer and Andrea Fuster, who are also both here today. And I'd like to start by giving you kind of an overview of what I'm going to talk about and an overview of the setting as well. So the setting will be Tensor gravity, and in a very general sense, you might say that Tensor gravity is the study of Tensor space-time geometry. So the idea here is that we would like to construct a theory which is, as best as possible, close to the structure of general relativity, but with one major change, namely that we modified pseudo-Riemannian geometry, or we extend it, I should say, to a more general geometric framework, which we call Tensor geometry. And there are various reasons why you might be interested in a theory like this. For me personally, the main motivation comes from quantum gravity phenomenology. So if you look, for instance, at models involving modified dispersion relations, Lorentz invariance violations, deformed Poincare symmetries, all these models seem to have the common rule that in order to describe them, you need some kind of geometric framework which is more general than pseudo-Riemannian geometry. And that, to me, is a clear sign that we should really try to understand theories like this, where this is exactly the point. We try to keep the structure of a theory that we know very well, but we try to incorporate these more general types of geometries. And then, in a certain sense, Tensor geometry is only the first step of doing this generalization. Although, in another sense, there are also arguments that it will be very difficult to go beyond Tensor gravity while still keeping the structure of general relativity. So that's why I think this is really important also in the context of the topic of this cost action. Of course, a very important ingredient in such a theory is the field equation, which relates the matter distribution in the universe on the one hand to the space-time curvature. And in this context, this field equation should be an extension of Einstein's field equation, right? We cannot just simply use Einstein's field equation because it's in general ill-defined on Tensor spacetimes. So we need an extension. And for us, the starting point will be Pfeiffer and Wolfhardt's field equation in vacuum. Our aim was to be able to say something about solutions to that equation. And well, in general, this is very, very difficult. This is already in general relativity, of course, very difficult to really say something in general about solutions. And here this becomes even worse because we have twice as many degrees of freedom because we have this Tensor space-time geometry, and also the equation just becomes a lot more difficult. So what we did, and this is going to be the main point of the talk, we tried to look at a certain particular type of Tensor geometry, which goes under the name parallel Randers geometries. I'll of course explain these notions later. And then we classified all solutions of this type to the vacuum field equations in Tensor gravity. And what we found was that, in fact, there is only one unique solution, or perhaps I should say a unique class of solutions of this type. And this is what we call the Randers PP waves, because they very closely resemble the well-known PP waves from general relativity. So this is an overview of what I'm going to say. I will be starting with Finsler geometry, some basics on Finsler geometry in a moment, and introduce these notions. And then, yeah, this will cover roughly half of the talk, I think. And then in the second half, we'll start from Wolfhardt's field equation and see how this leads for these kinds of geometries to this Randers PP wave solution. The main way in which Finsler geometry generalizes Riemannian geometry is that the usual geometric objects generally become functions not only on the point in the manifold, but also on the direction. And we denote this as follows. So suppose we have coordinates x on our base manifold. This will be space-time. Then this induces coordinates on the tangent bundle, which we may denote by x comma y. So then x denotes a point in space-time, and y denotes a tangent vector at the point x. So you can think of this y as a velocity, for instance. You might also think of it as a momentum. We formulate this on tangent space, but you might also think about it as a momentum. So this will lead to some kind of geometry on space-time, which somehow depends on the momentum. And so the usual geometric objects will become functions of x and y. And a very important example of this is the generalization of the Riemannian metric, which we usually call the fundamental tensor in Finsler geometry. And this thing becomes a function now of both the position and the direction in your space-time manifold. Usually, however, we do not start from this object, and we consider this a derived object, derived from the so-called Finsler function. So the Finsler function will be our basic starting point, and it's nothing other than just the infinitesimal line element. So the idea is that we say, suppose this line element is given by some generic function on the tangent bundle, then what are the minimal conditions that this f should satisfy in order that this leads to a natural length measure and a natural geometric structure? And the answer to that is exactly given by the axioms of a Finsler space, which I'll show you on the next slide. But one more thing, so I said this Gij is a derived object. We will define it on the next slide in terms of the Finsler function. And then if we do it in the right way, we will still have this formula, which is exactly the same as the one in Riemannian geometry, except that now this Gij depends also on the direction. So this is the formal definition that we will use. A Finsler space is a smooth manifold endowed with a function on the tangent bundle that satisfies these three axioms. The first one is homogeneity, and this basically translates to the condition that if you have a curve on your manifold, then the length of that curve is a geometric quantity. So it's independent of the parameterization of the curve. And that's very important from a physical point of view, because this is exactly what allows us to define the proper time of an observer, of a clock. This is usually defined as the length of a world line, right? And so this is, well, this is very important if we want to keep the structure of GR. Then we usually want f to be smooth. That's reasonably straightforward. And thirdly, this is how we now define this generalization of the Riemannian metric. So we take two partial derivatives with respect to the tangent space arguments of the squared line element, and that gives us this generalization of the Riemannian metric, and that's why we require this to be positive definite. Let's have a look at an example. So this is also an example which will be very relevant for our Randers PP waves, as the name suggests. So the construction is simple. We define our Finslerian line element by starting from a Riemannian line element. So Aij here is a Riemannian metric, and we add to that a linear deviation. So alpha is this Riemannian line element, beta is some one form, and this is how we construct the Randers metric. We want to change one thing, however, because we want to describe space-time geometry, not just positive definite geometry. And so what we would like to do is change this signature to Lorentzian signature. There's a problem with this, and without going to the details, we have to modify some other part of the definition as well. So what's very often done is that we say, okay, let's not require the Finsler function to be defined on the entire tangent bundle, but perhaps just some conic subbundle of the tangent bundle. And very often this will be the inside of the light cone, so the time-like directions. So this is what we will take as our definition for a Finsler spacetime. And then also in the Randers metric, we want to start from a Lorentzian line element rather than a Riemannian line element. Okay, so I want to discuss one more property of Finsler spacetimes before we go to the field equation. And this is the Baerwald property. Okay, let's start with Lorentzian spacetimes. And by Lorentzian, I mean non-Finslerian, right? So just a classical GR Lorentzian spacetime. We all know that there exists a unique torsion-free, a unique torsion-free, metric-compatible linear connection on the tangent bundle, which is just a Levi-Civita connection. And we can kind of generalize this to Finsler spacetimes, but not exactly. So we can still define a canonical connection which has these two properties, metric compatibility and torsion freeness. But in general, this connection cannot be, will not be linear. However, sometimes it is linear, and this is exactly the definition of what we mean by a Baerwald spacetime. So you might say that a Baerwald spacetime is a Finsler spacetime which has a linear Levi-Civita type connection. And these spacetimes are very nice because you can actually do computations with them without, without needing tons of paper. Okay, so we have seen Randers metrics, we have seen the Baerwald property, and now we want to combine those two properties because in the end we want to look at what we call Baerwald-Randers spacetimes. So what do we know? Suppose we have a Randers metric, which already introduced, and there is this nice characterization, which is well known in Finsler geometry, that such a metric has the Baerwald property if and only if the one form is parallel or covariantly constant with respect to the Lorentzian part of the Randers metric. So that is, if and only if this condition is satisfied, where this LC stands for the Levi-Civita connection of the Lorentzian part alpha. And if we have this, if we have such a Randers space which is Baerwald, then it also follows that in fact the connection on the Finsler spacetime coincides exactly with the connection on this alpha. So that's very nice, especially later when we'll look at the field equation. We can relate the field equation on Finsler spacetime to actually some kind of field equation for this Lorentzian part, which will of course be a lot simpler. And that's in fact what we will do now. So this was our starting point for our research. We thought, let's start with this equation. So this is Pfeiffer-Wohlfarth's vacuum equation for Finsler gravity. I'm not going to explain all these objects in detail. For our case, a lot of them will vanish identically anyway. But this is an extension of Einstein's field equation. So if we, question. So you can start with the Einstein-Hilbert action and then write you can kind of lift that to Finsler spacetimes.
Splitting up is not trivial, right?
It's not?
I mean, this is kinematics. Up to now, you study kinematics of Finsler geometry.
Yeah.
Now, putting a theory, different things of how you are going to set a junction. Okay, we can discuss it.
Yeah, okay. I don't understand your question entirely, but we'll discuss later. Yeah. So what I was saying is this is an extension of Einstein's field equation in the sense that if we now put in a Lorentzian metric here, then this will simply reduce to Einstein's field equation in vacuum. But in general, it's very, very complicated. And so in order to be able to say something about its solutions, as I already alluded to, you need to impose some conditions on your spacetimes. And first of all, we can look what happens when we consider Baerwald spacetimes. then this whole part over here vanishes identically. So that means that all these S mu, S nu things apparently have something to do with the nonlinearity of the connection. And for Bellot space sizes, we have a linear connection. These all vanish identically. But still, this is not a nice equation that you would like to solve. So that's why we also looked at Randers metrics at the same time. And when you do that, we proved that, in fact, this whole equation simply becomes equivalent to the vanishing of the Finsler-Ricci tensor, which is great because this is the formal analog of Einstein's field equations in vacuum. It's not exactly the same because we're still, this thing is in general still defined in terms of the Finslerian connection and not some Levi-Civita connection of some Lorentzian metric. Although I showed you some slides back that, in fact, we do have this in this case. So our Finslerian connection is just the Levi-Civita connection of our Lorentzian part, and that means that we can even have this equivalence. So what we have proven now, essentially, is that the vacuum equation in Finsler gravity for these Baerbold-Randers spacetimes reduces to Einstein's original field equation for our Lorentzian part. And this is what I summarized here in the theorem. For now, this part in parentheses is not relevant. We're going to add some conditions later. And then this will become relevant. For now, this holds in general. So a Baerbold-Randers metric is a vacuum solution if and only if the Lorentzian part is a solution in Einstein gravity, which is very nice. However, we cannot just pick any alpha, although it might seem like this, it might seem from this and that we could pick any vacuum solution alpha. We actually, in the premise of our theorem here, we're looking at Baerbold-Randers spacetimes. And if you may remember from an earlier slide, a Randers metric could only be Baerbold if the one form was covariantly constant with respect to alpha. So we can add this condition here for free already. And this restricts the choices for alpha quite a lot. And in fact, there's a theorem by Battista which says that in 4 dimensions, so this is where this becomes important, in 4 dimensions, if you have a vacuum solution to Einstein gravity which admits a parallel one form, then essentially this one form has to be null. There's one other case in which alpha actually is flat Minkowski space, so that's why I put non-trivial here. We will neglect that situation for the purpose of this talk and only look at the non-trivial case, and then we have these 3 conditions. And some of you might perhaps recognize these conditions. This is exactly the definition of what we call PP waves in general relativity. So the PP wave is a metric in general relativity which is defined by its property that it admits a parallel null one form. And there is a lot known about these metrics, and you can always write them in this form. So in preferred coordinates, this is the metric that our Lorentzian part will need to have. And let's quickly see why this actually might constitute a PP wave, a gravitational wave. So if you think of this function h, let's for a moment consider the situation where this function vanishes. Then actually we're simply in Minkowski space. So this u and these v, we call them light cone coordinates. And if you substitute that here, then we see that without the function h, we're simply in flat Minkowski space. However, if we put this h here, then we have apparently some disturbance on Minkowski space. And the fact that it depends only on u and not explicitly on t and x3 means that this disturbance travels at the speed of light in the x3 direction. And so that's why, at least intuitively, this has the interpretation of a gravitational wave. And in these coordinates, the parallel null form is simply given by du. Yeah, and we of course want this to be a vacuum solution, and this is exactly the condition for that. So now we can put all of this in, and this was our final result. So any 4-dimensional, non-trivial Baerbold-Randers solution to the vacuum field equations in Finsler gravity has to be of this form. So it's a Randers metric by definition, where this Lorentzian part has to be this PP wave metric that we've just seen. And the one form has to be the defining covariantly constant null one form. And then we put here a vector lambda in front because probably if we want to do some phenomenological calculations, we want to have a spacetime which is close to the Lorentzian PP waves. And we can put all of that in explicitly, and then this is the final result for the Finslerian spacetime geometry. Then the obvious question, of course, becomes how should we interpret this? And this is something that I realized only when we found this solution. I was like, okay, now this is great because now we can try to extract some phenomenological consequences from this and really calculate some observables. And then I realized that this is something which is just not really understood very well yet, how to do this. So I cannot give you the answer to that yet. I think this is a very important next step that we have to take, and it's something that we're currently working on. So perhaps at the next annual meeting we'll be able to tell you our progress. But for now, thank you very much for listening.
Thank you very much, Sjors. The question I wanted to ask you is exactly what you expressed at the end. I mean, I could follow the maths, but I lack the intuition on how to verify or how to falsify that this approach is correct. Though you have not developed the phenomenology yet, could you provide us? I'm an experimentalist, so I may help in developing the phenomenology. If I get a kind of intuition on what is changing in this model with respect to standard relativity. So could you give a hint on really what's different here?
Okay, so one thing that changes that we actually do know, one of the few things that we do know, is that, for instance, in general relativity, when you consider a world line of an observer, then the proper, well, you parameterize the world line with respect to proper time by setting your line element equal to 1, essentially, right? And what changes here is that our line element, which is f, now gets an additional vector. So the canonical normalization of the world line will change by this vector, which if lambda is really small will be a very small difference. But this will probably result in some differences in the proper time that an observer measures between events. That's about as far as I can go at this point. The rest is very unclear to me at this point.
Okay, thank you very much. More questions?
Okay, my question was the following, that if you have the geometry, so for instance, Riemannian geometry, you have the kinematics, you know the structure of the geometry. However, what theory you are going to build on that is a different thing. You can have, for instance, GR, you can have Gauss, Bonnet, Lovelock, all this kind of stuff. So these are different theories on the same geometry. So my question here is that, okay, we have an extended geometrical structure and we know the kinematics. Now, what will be the action of this theory? This is something that we were discussing with Christian and Nico, because it's not trivial. I mean, okay, we know that we need a generalization of the Einstein-Hilbert action, but this is not trivial. For instance, you have the structure, you have the R tensor, you have the S tensor. So perhaps you can beat the Lagrangian made from all of. So in your particular example, what was the action that led to these field equations?
So these field equations by Pfeiffer and Wolfhard, they were originally derived by starting from the Einstein-Hilbert action, which you can in a canonical way generalize to French-Smith spacetimes. So essentially you still take the integral over the Ricci curvature. And if you do that, then your field equations will be exactly the one that I showed you. But you can also do it in a different way, which I personally really like. So you can start from the geodesic deviation equation. And this is more like a physical way to think about it, in exactly the same way as you can use that starting point to arrive at Einstein's field equations, just following the exact same steps and requiring that this is a variational equation also leads to this equation. So yeah, I don't know if that answers your question.
I just want to comment on this question on phenomenology. We saw the talk by Yali Lobo on 2 days ago, I think, yes. And yesterday we had the nice talk about the neutrino the muon lifetime measurements. Yeah, and this is all things which you would find also in this Finsler geometry, or which you can describe by Finsler geometry, that you have this modified length measure, which is your intrinsic clock, which defines the proper time, as Sjors said, and then this would have effect on the time dilation effects, definitely. So you would see a modified muon lifetime compared to the lab frame and the rest frame of the muon. And this should be in principle detectable, and one could set bounds or evidence for such a modification.
Great, thank you very much. Yeah.
I would like to ask about this. So the theory is not relativistic if you find a different time lifetime in different frames. Yeah. It's just time derivative.
Okay, if there are no more questions, let's thank the speaker again. And now we have Nicoleta Voicu. That will tell us about relativistic kinetic gases as direct sources of gravity. So please, Nicoleta, go ahead.
Just trying to adjust this.
Yes, yes. Take your time. Sorry.
Maybe. Okay, am I hearable?
Yes.
So first of all, I would like to thank the organizers for giving me the opportunity to talk here, and also for the absolutely amazing organizing of this conference. My talk is very much related to the previous one because it deals with the same geometric setting, and I might even try to answer a bit further Manos's question about action and how it is constructed. This is a joint work with Christian Pfeiffer with Manuel Hohmann. And I would have to first give a caveat. It's very much in its beginnings, this work. So I'm just going to set the basis. This is work in progress. The main idea of the talk is the following. We propose a Finsler geometric model for the description of a gravitating multiparticle system viewed as a kinetic gas. And our argument is that if you regard the kinetic theory of gases, then Finsler geometry is the most natural geometric framework for modeling, for coupling to gravity, such a thing. And the main advantage is that this way we can take the full velocity distribution of the sources into account. So if you have many sources moving with different velocities, then that's the way to proceed, the best way to proceed. This is our argument. And of course, our great hope is that it could account for at least a part of the dark phenomenology. As references for the moment, we just have these. This is from last year. This is the main paper with the technical details included. This is more essay-like. And, well, these being said, I'm going to go to the technical details of the story. And first of all, I would like to continue what Sjors already had said, some like take-home ideas on why should we use at all Finsler geometry. Who ordered Finsler, to cite someone? I don't exactly remember the name, but it was quite a famous physicist that asked. Okay, who ordered Finsler? And first of all, because we are here, the first argument to give is modified dispersion relation. So once we have modified dispersion relation in a way or another, and we want an arc length to be defined, this is Finsler. Actually, to be accurate, it's pseudo-Finsler, because if you say Finsler, a geometer would understand positive definite. So it's pseudo-Finsler. like pseudo-Riemannian, but we usually refer it in a non-rigorous way as Finsler, that having a modified dispersion relation, you end up with a line element given by a function of this type, of course, depending on the mass here. And here, this is just a bit of a digression to remind how this relation is established. The construction of this Finsler function is given by the so-called Helmholtz action, where here you have lambda Lagrange multiplier, and here basically you have your dispersion relation insured. So f is either, say, the difference between h and m squared or some logarithm of the ratio, something that vanishes once this relation is satisfied. So once you vary this with respect to p and lambda, then you eliminate them and you end up with sh being expressed in terms of xx dot. And basically you take the integrand and that's your Finsler function. So that's how it goes for modified dispersion relation. This is the first main argument, but there's more to it than this. And my talk is going to deal with these other reasons. Here, to actually continue the previous idea, if you have, for instance, not necessarily modified dispersion, modified special relativity, but standard model extensions based on Lorentz invariance variation. So anytime you have something else than the local Lorentz symmetry, you end up with Finsler. Then there is another argument based on the fact that if you want to extend the Euler-Spirani shield axioms for GR, there's one axiom which is not necessarily there, which is smoothness of the metric tensor in the end at the origin. Then you end up again with Finsler, and this is work by Perlich and Lammerzahl. And here is the idea that I'm going to present. And my main argument, Finsler geometry can provide a more accurate description of gravity, taking into account multiple sources moving with different velocities. And I'm going to point out a main feature of pseudo-Finsler geometry. This is the most general geometry with a geometric clock. So if you want a clock postulate, like proper time between two events is given by the length of the world line, then you need a well-defined notion of arc length. So if you want a well-defined notion of arc length of a proper time, there's no going beyond Finsler, like no going beyond Hornbesky. So you really need Finsler geometry if you want to have a geometric clock. And I'm going to recommend for a review the one written by Christian in 2019 in Journal of Geometric Methods in Physics. Now passing to our story, kinetic gases. By kinetic gas, we are going to understand a large enough number of interacting point particles described by a smooth one-particle distribution function. So basically, this is the picture. Kinetic gas is a number of particles moving, each one with its velocity, and it is described by such a function, which depends in principle on the positions and four velocities of the particles, compared to the idea of perfect fluid, where basically you take just the average velocity. So they are roughly considered to go in the same direction. In the kinetic gas, this is not necessarily the case. So we have this guy to describe a kinetic gas, and what it does is to basically count the particle trajectories crossing a hypersurface of the so-called observer space. Observer space is this kind of guy. So it's made of pairs, position and velocity, where the velocity is normalized and future pointing. So there are basically positions and velocities of massive particles. That's observer space. And one particle distribution function counts these trajectories that cross a hypersurface. That's a region of space-time and a certain range of velocities. This is known actually in GR. There's a very nice review by Sarbach and Tsanias. There are actually multiple reviews. Coupling to gravity in general relativity, when you deal with kinetic gases, goes in the following way. First, you average over velocities, over all possible observer velocities, and you get the energy momentum tensor. And then you use Einstein equations. So that's how it goes in general relativity. One more point to stress here is that for collisionless gases, the number of particles getting into a region of the observer space and the number of trajectories, so sorry, not particles, getting out, it's the same. So you have kind of conservation, which is expressed in terms of Liouville equation. So phi is conserved along geodesics. I'm going to really introduce this guy. It's called the Reeb or geodesic vector field. So the whole thing, anyway, even in general relativity, is treated at the level of tangent or cotangent bundle. And this is the geodesic vector field which lives on this bundle. Now, what is our idea, the Finslerian approach? As I already pointed out, we want to couple gravity directly to phi. So we want to skip this averaging over velocities. And the first remark is that this coupling should then take place on the same space where phi lives. That's basically the observer space, which is a subset of the tangent bundle of the space-time manifold. Or it can be treated similarly on momentum space. This is still to be done. It was easier to treat it on the tangent bundle for the moment. But the tangent bundle, I'm going to recall, is a set of all pairs. It can be identified with the set of all pairs made of points of the manifold and vectors in the tangent space. So it's basically position and velocity space. So this is what we want to do, to couple directly to gravity and where phi lives. That's on the tangent bundle. And a first remark is that phi is a scalar function defined on some subset of this tangent bundle. That's exactly where the Finsler function lives. It's again a scalar equation on the tangent bundle. So if you use this as your dynamical field, you'll end up with a scalar equation on the tangent bundle, just as phi. So this seems quite natural to think of, okay, this should go this way. We should couple there. So it's very nice if we can have some field equation on the tangent, some scalar field equation on the tangent bundle. So that's what we are going to do. And for the rest of this talk, by M, I will mean a four-dimensional connected orientable manifold, and x mu, x dot mu will really just mean coordinates, no parameterized trajectory. This is just a notation for tangent vector coordinates. And I'm going to introduce Finsler spacetimes. Thanks, Sjors, for already doing it. I'm just now going to be a bit more nuanced. As Sjors already mentioned, in the case of Finsler spacetime functions, we might be not able to define the Finsler function on the whole tangent bundle, but just on a subset. And this subset must have some properties. It must be a so-called conic subbundle. That's basically a subset of the tangent bundle where in each tangent space you have at least one vector. So at each point of the manifold, there's at least one vector in your subset Q. And once a vector is there, then any positively rescaled vector should be there. This is essential when we deal with homogeneity, to have well-defined objects. So if you want, for instance, the metric tensor to be defined at some x, you want it to be defined at all along the whole half line. So we assume this definition of conic subbundle. With this, by a Finsler spacetime will mean a pair where M is a manifold and L is defined and smooth on a conic subbundle A, which we will call the set of admissible vectors, with the following properties. This is 2 homogeneity in the vector. This will ensure the definition of arc length, that it's correct and independent on parametrization. Then we want the Hessian, which will play the role of metric tensor, so to say, to be non-degenerate on A, and only Lorentzian on another subbundle of A, which we identify as our future directed time-like set. So basically, to what Sjors said, we nuance a bit. We might have L defined on a larger set than the one he denoted as A, which is our T. So we must have a conic subbundle T in A, on which L is positive, has Lorentzian signature, and the boundary of T has to be null. So L has to be continuously extended as 0 to the boundary. So this is the interpretation of the quantities that we have introduced. Basically, L provides your ds squared interval. It's expressed in terms of G mu nu this way, just adding to the Riemannian geometry with the difference that here G mu nu depends on x dot. This is how we express the length of a curve, where f means the square root of the module of L. So basically, it's the square root of this guy. And I have to stress this is independent of the choice of the parameter T due to homogeneity. So this is essential. And here is a more accurate picture of the sets we have described. So L has to be defined and smooth on some set. Here is everything outside the red regions. This A, T is a subset of the set of admissible vectors. So it will be basically in the inside of this cone, and it's interpreted as future pointing time-like cone. And inside it, we have the observer space, which appears also in Riemannian geometry, in pseudo-Riemannian geometry. Just here, OX is expressed in terms of L. So in principle, we take Fanias and Zarbach's model. So lift everything to the tangent bundle, work on observer space. Just here, observer space is defined in terms of L. So here, red areas are non-admissible. So you can see, for instance, in this particular case, inside the cone, everything goes smoothly. It's fine. It's Lorentzian. On the boundary, we have maybe just continuous extension. But with this, causality properties are ensured. And here are some examples. Here I've expressed everything in terms of S as it's more common. You can alternatively work in terms of L. The simplest example of Finster spacetimes are Lorentzian spacetimes. Here A denotes a Lorentzian metric. Then a next class is given by Randers spacetimes, already presented by Sjors. Then there's Bogoslovsky-Kropina metrics, which are the base for this very special relativity. You have to, I would recommend Cohen and Glashow's paper for this. So you take a power of this Lorentzian norm, pseudo-norm, and deform it via a one form. And you get very special relativity as a consequence. Then another model can be fourth root metric. So you take as your f the fourth root of some fourth degree homogeneous polynomial. For instance, take a Lorentzian metric and another Lorentzian metric, take the product and then the fourth root. Basically, the cone that I presented here is the cone of a quartic metric. So you have two light cones, and this corresponds physically to birefringence. You have two different speeds of light. So this can be also the case. So these are the main examples. Geodesics and geodesic deviation, everything can be treated in a very much similar way to Lorentzian one. And I promised to introduce the Reeb vector field. So for those who have ever worked with compact geometry, Reeb vector field might ring a bell. It's expressed in terms of these geodesic coefficients. You can think of these as Christoffel symbols contracted by the velocities. So indeed, once we have a Spinster space-time on the observer space, we really have a compact structure which gives us a whole rich geometry, and which I skipped here. So the details can be found in the paper, but it's really used. Now how we do build the kinetic action. Thanks. Consider a hypersurface, and these are, say, particle trajectories crossing it, and each particle evolves according to its proper time, and you just stop the clock at some moment t. So you have particles evolving according to their proper time. They describe at value of the parameter t another hypersurfaces, and you build a volume in the observer space this way. Again, the number of particles crossing sigma is given by integrating the one particle distribution function. Here, the canonical volume is obtained from L. Then we introduce a similar argument to the one in GR. Actually, sorry, it's just here introduced. The number of particles is similar to the one in GR. Action most intuitively can be constructed as, imagine that all those particles have the same mass m. They will have a number n of particles, and you build a hypersurface as before. So t is a fixed value of proper time, and re-express this in terms of the Finsler function. You end up with a guy like this. So with some computations, the action for such a gas is the mass times the integral over a hypersurface of the 1 PDF. This is one argument. Some other argument can come from the Liouville equation, and I'm going to stress it a bit later. Now, if we constructed the matter action this way, first thing to check is what does coordinate invariance imply, because the number of particles is coordinate invariant. So our action has to be coordinate invariant. And it does indeed imply something like an average conservation law. Here, that's a covariant derivative with respect to any of the standard Finslerian connection. It's the same. So you get the same expression of this guy, which we call the energy momentum distribution tensor, in like one particle distribution function. And this guy depends on positions and velocities. Here on the observer space, L is 1. I just put it for technical reasons, because when you go to action, you'd rather work in terms of projectivized tangent bundle. This is a technicality. So here you just can think of L as being 1. So this is the so-called energy momentum distribution tensor, and as a consequence of the coordinate invariance of the action, you have such an average conservation law. So at each point, basically, this guy is conserved. And indeed, in the particular case of Liouville, collisionless gas, you have the Liouville equation again. So postulating the Liouville equation, it actually is equivalent to the pointwise conservation of this guy, of the energy momentum distribution tensor. And really proceeding again via inverse problem of variational calculus, you will end up with the same phi as your integrand in the action for the matter. And this is the total action, and it's related to what Manu says. So we build as the vacuum action, we take the so-called Finslerian Ricci scalar. It's not exactly the Ricci scalar of a connection, of any connection. You take geodesic deviation. That was the argument in our 2019 paper. So take as a postulate that in vacuum, geodesic deviation has a vanishing trace. This is Euler-Spiranian shield. But this doesn't turn out to be variational. So there's an algorithm called variational completion. The closest equation that is variational is based on this action, and it is indeed Pfeiffer-Wohlfahrt equation. This is for vacuum. Then add our matter term, we end up with this guy, where here G is a scalar. This is what you already saw in Sjors' talk. This was denoted by S. Just to have an intuition, R is Ricci scalar, and P is a non-Riemannian quantity. Here you can see the derivatives with respect to x dot of the determinant of G, so the thing that gives you the volume element, and their evolution along geodesics. This is a non-Riemannian quantity which appears. So to conclude with this part, what we want to do is to compare this system that we have obtained with Einstein-Vlasov equation. Here we have obtained the gravitational field of a kinetic gas with no averaging over velocities. And the next step is indeed to define for, in principle, any given Wieslerian metric, to define an algorithm to find a Riemannian metric and plug it into the Einstein-Vlasov equation and compare. Of course, we expect to find some extra terms like, say, cosmological constant or whatever. And the next step will be to also apply this first to cosmology. We have, for the moment, we know how the most generally cosmologically symmetric Tensor space-time function looks like. It's a combination between, this is Friedmann-Lemaitre-Robertson-Walker line element, just translated into tangent bundle language. So this is Robertson-Walker metric and T dot. So it's quite constrained, but still it leaves a lot of room to proceed. And of course, we want to find a reasonable cosmologically symmetric 1 PDF and integrate the resulting field equation, then tackle spherically symmetric solutions with appropriate 1 PDF function phi. So this is the first candidate. This is still work in progress. So here it is, and some references. Thank you.
Thank you very much, Nicoleta. I have myself a question. In this era in which we are moving from, say, observational cosmology to observational cosmonomy, because we have precision measurements on cosmological observables and therefore on structure formation in the universe at shorter scales and longer scales. These modifications of the kinetic behavior of gases due to modified gravities probably are already constrained, or there are results. I'm not very familiar with that. So if there is any cosmologist in the room that can confirm whether there are constraints, that would be nice. But my only question is, when you now choose the paths that you were discussing in your last slide on how to continue the work, would you look at the literature concerning experimental constraints that are already there and may make change
we want
your decisions?
The first thing would be to, I have a quite good intuition of how 1 PDF for cosmology would look like. It's quite intuitive. It has to obey the same symmetry. But yes, of course, we will look at the constraints. But first thing is to just really solve the field equation, sit and solve the field equation for such a phi. So after we have this, we can indeed talk about constraints and see whether it's viable or not, whether it fits into the constraints, of course.
Okay, thank you very much. Any other question or comment? Yes.
Hi, Nico. I'm not sure whether this question is trivial or maybe it doesn't make sense at all, but what is a particle in your system?
Well, it depends on the physical system you look at. If it's in cosmology, then that's, say, stars or galaxies.
It wasn't clear enough to me, so.
Yeah, so it depends on the scale you're looking at.
But it could also be something else then, for instance?
We didn't think of quantum for the moment. So if this is your question.
No.
So it's classical. It's.
I'm just wondering.
Yeah, it's something that you can approximate as a point particle.
So in shorter scales, that could be the gas that collapses producing a star. So
yes.
From a star formation, you may get constraints that affect this model.
Yes, again, maybe, hopefully next year I will have a solution, or one cosmologically symmetrical solution and one, say, spherically symmetric. And then we can really talk and Yes.
Okay, thank you very much. Any other question or comment? Yes.
Well, your question is that Riemannian geometry is a subclass of Fischler geometry. So we know at least one case that this works. So the structure is a bit more complicated. So we will leave the data to tell us whether this deviation is
Sure.
is allowed, is satisfied in nature. But the structure has not any problem.
Yeah, sure.
Including Riemannian geometry.
So at a certain point, you showed that there was a cosmological constant. Does it appear more naturally here than in Einstein general relativity? Or?
Yes, that's our hope, to have it basically in the geometry, not just add it by hand. That's our ambition. Of course, there will be some difference
Okay, but
here, of course. So there, it can be assimilated with a cosmological constant, but we don't know how big it is, if it really will fit observations in the end. So that's something that we are not yet comfortable with, because we don't know how much of the dark phenomenology is really modeled by such a thing. But our hope is that, yes, so there will for sure appear something like a lambda from the geometry.
Great. So, okay, Christian.
Yeah, just a quick comment on the question. So here the idea is, I mean, the kinetic gas, when you look just at the description of a kinetic gas in general relativity, yeah, there you already have this one particle distribution function description, which gives you accurate dynamics of a gas without coupling it to the geometry. And when you derive the gravitational field of such a gas, you average out all of this geometry, velocity distribution. Yeah, that's exactly this energy momentum tensor which Nico displays there. And now the idea is that we also describe gravity on this kinetic level, so on this velocity dependent level. So we have a gravitational field distribution, which is sourced by a kinetic gas or one particle distribution function. And then when we average the right-hand side, so when we average the one particle distribution function, we get the energy momentum tensor, that is S here. And then maybe also when we average the gravitational field distribution described in terms of Finsler geometry, then we also get maybe the Einstein equations or the Einstein equations plus correction. So the idea would be that the cosmological constant is some kind of velocity averaging effect here, which absorbs this. But this we cannot do. We have no way at the moment to make this mathematically precise. This is the idea, and at the moment we are working.
Yeah. So we have, sorry for adding some more. We can get also in Finsler geometry an energy momentum density in the same fashion as in Riemannian geometry. But here, typically, we cannot undensify because this guy depends on x dot. So we have a precise idea of what's going on the right-hand side. We can average velocities out, and you get energy momentum density on the base manifold.
Okay, thank you very much. If there are no more questions, let's thank Nicoleta again.
Yeah.